we view the world and the outcomes we come to is often a function of the perspective we have from where we're standing and from where we're looking. How something appears is always a matter of perspective. As I've grown older, I've learned to tolerate ambiguity better and to realize that people can be right about the same thing in different ways. Today, we're not going to talk about how we come to different conclusions from different perspectives, but rather how we can come to the same mathematical conclusions with different approaches or perspectives. We'll start off by looking at the context of sharing a chocolate. So, three friends, Lisa, Aldi, and Glynis, wish to share this chocolate. It's difficult to break a chocolate into three pieces, so what they do is they break it into four. Each of them has a piece, and then there's a piece left. It's difficult to break that piece into three, so they break it into four. Each of them has a piece, and there's a piece left. Each time they continue, just proceeding with the new piece of chocolate as a sort of chocolate in its own right. At this point, you might say, does it really matter to keep on breaking it up and sharing this tiny, tiny little piece of chocolate? But after all, it is chocolate. So now let's take a look at what happens here. What we would expect, just intuitively, non-mathematically, we would expect that if they continued in this vein, that each of them would end up with a third of the chocolate, or a limit that would approach a third of the chocolate. If we look just at Lisa's share, Lisa gets a quarter of the chocolate, then a quarter of a quarter, then a quarter of a quarter of a quarter, and so on. And so if we add up Lisa's share of the chocolate, it's actually a geometric series with a common ratio of a quarter, the first term of a quarter, and the sum to infinity, which will converge because r is a quarter, which is between -1 and 1. The sum to infinity comes to a third. I think it's quite comforting that the sort of infinite geometric series gives us the same answer as our gut feel on this chocolate problem. Next up, we're going to dive a little bit into fractions, and we're going to just look at a couple of things. Interestingly, our Casio calculator, if we type in 0.373737 for a few times, it tells us that the answer is 0.3737, which is what we would hope. Interestingly, if we add in one more 37, it now tells us that is 37/99. It's actually not 37/99, right? We would need to type those 3 sevens forever for it to conclude that it's 37/99. What we're going to do now is we're just going to explore a little bit rational numbers and fractions, and investigate a little bit about which ones end and which ones repeat. So here you'll see that we've got an Excel spreadsheet, and we've worked out over here 1 divided by 23, the reciprocal of 23. Right, at the moment it seems to be about that. If we opt to increase the decimal, eventually Excel tells us that in fact it seems to terminate, but in fact it actually doesn't. On the next page of the spreadsheet, what we've got here is a sort of heartbeat of a fraction where we can type in a denominator. So let's type in 23. And what we'll see is that in fact 23 doesn't terminate, but it repeats. And we can see this little kink in the graph over here, and it actually repeats after 22 decimal places. Sevenths, as we might know, are cyclical as well. They repeat in their decimal places after 6 decimal places. And in fact 13ths, one might have thought they might repeat after 12, but in fact they repeat after 6 as well. The interesting thing is kind of which ones end and which ones repeat. These are all rational numbers. So if we typed in something like a 25th, we'll see that in fact it terminates. It terminates at 0,04, whereas something like a third repeats. Okay, so some rational numbers repeat and some terminate. And the interesting thing is kind of which is which. Another interesting thing is how long a sort of sequence of repeating can we achieve. So this is 1/97, and I believe I'm right in saying that it hasn't repeated yet, but it will repeat if we just extend the capability of this formula here. Right, so an obvious next question is which of these numbers will end and which will repeat? Well, the secret lies in looking at the prime factorization of those denominators. Something like 1 over 1250, the 1250 can prime factorize to 2 times 5 cubed. Now, 2 times 5 cubed we can make into some tens here, and I see I've actually messed up we wouldn't multiply it by 2 cubed. In fact, we'd multiply it by 2 squared over 2 squared. When we do that, we will actually get 4, so it should be 4 over 1,000. Now 4 over 1,000 clearly terminates, should be 0,004, right? Because we can make the denominator into a power of 10, all that's going to happen is that the decimal place is going to move and the thing will terminate. Contrast that with 1 over 150. 150 can prime factorize into 2 times 3 times 5 squared. And while that 2 on the denominator can be made into a 10, and the 5 squareds can be made into a power of 10, 3 cannot. And because of that, 1 over 150 will in fact repeat rather than terminate. Let's just confirm that. There we go. It repeats. It's actually 0,06 recurring, and the 6's carry on forever thereafter. Now, one of the skills that we want learners to be able to do is to be able to take a recurring decimal and express it as a ratio of two whole numbers, which we obviously can as it's a rational number, right? And as we've shown, the calculator actually does this erroneously but quite helpfully. We'll remember that we often do this with grade 8s. We let x be 0,373737. Then 100x is exactly the same number, but with 37 added to it. When we subtract those two numbers, we get that 99x is exactly 37. All the stuff after the decimal point is exactly the same, even though it continues indefinitely. And so x is in fact 37 over 99. I want us to look at a different way of approaching the same thing, and that's to realize that this infinite decimal representation can actually be written as a geometric series, right? And once again, we've got an infinite geometric series with a common ratio of 100th, and because that common ratio is between -1 and 1, that series will converge, and we can use our sum to infinity formula, and lo and behold, we end up with exactly the same answer of 37 over 99. Right, one of the things that's always intrigued me is that we teach students that something like y equals 2x plus 3 is a straight line with a gradient of 2 and a y-intercept of 3. But do we in fact go the other way around? In other words, do we show them that if a line has a gradient of m and a y-intercept of c, that it can be written in the form y equals mx plus c? So this is just sort of doing something slightly differently, sort of going the other way. And the secret really lies in locus for those of us who taught it all those years ago. But we want a point on this line that will ensure that we have a gradient of m when we use these 2 points. So in other words, the point xy and the point 0c. So if we just use our gradient formula, and then we multiply both sides by x from the denominator, and then add the c, we get y equals mx plus c. In similar vein, here we've got a line with a gradient of m passing through a random point, just a random fixed point on the line. And we've got another point that we want to satisfy that that the line joining the points xy and x1, y1 has a gradient of m. So again, we just express this mathematically, and there we see that formula that gets provided on the formula sheet. This is actually the formula I prefer for straight lines. It's actually one line more efficient than the y equals mx plus c one. But I think really cool to show students where these formulas actually arise from. They weren't sort of discovered by someone. Sorry, they were discovered by someone. They weren't handed down on sort of stone tablets along with the commandments. Right, so just an example now, we're going to find the equation of this line in two different ways. And I think that the way most teachers are going to teach, they're going to work out the gradient, and then they're either going to use the y equals mx plus c or the y minus y1 formula, and we get our final answer. There it is. But another way of doing it, which doesn't involve working out the gradient at all using a gradient, is to just say, right, we know these points are going to lie on this line y equals mx plus c. Let's sub them both in, and we now have two equations and two variables. Those are easily solved by subtracting the one from the other, and we in fact get our value of m as 2. Happens to be the gradient, but in fact we don't need to know anything about gradient to have arrived at that point. And then when we sub that value of 2 in, we can get the c value. And not surprisingly, and quite encouragingly, we get the same result. I think this sort of different thinking around things is quite a powerful thing to do with students, as it helps build connections and helps them understand that there's kind of more than one way to skin a cat. I'm not sure why one would ever want to skin a cat. All right, so those of you who follow knockout tournaments will know that, for example, in the Grand Slams of tennis, there are 128 players in the first round, which means 64 matches. Then those 64 players play 32 matches in round two, half of the players getting knocked out each time. Right, we can work out how many rounds there are using a geometric series, a sequence rather, and we can also work out the total number of matches. And we get that the total number of matches is 127 when 128 players play. Now, there's a much easier way of confirming this and, in fact, of doing it, and that's to appreciate that every time a match is played, someone gets knocked out. We've got 128 people, and we want only one of them to remain. So we need 127 matches to eliminate all but the winner. Again, I think a nice sort of logical argument to support a mathematical calculation. Let's switch to a different type of tournament, and that is the whole idea of a sort of round robin tournament. And this is quite a common thing which we do in maths often. So I'm going to go through it quite quickly. But we could basically look at this thing in three different ways. The first team is going to play 7 matches. They don't play themselves. The second team doesn't have to play the first team or themselves, so they play 6 additional, etc., down to 1. So that's going to be the total number of matches. Another way of looking at it is to say, well, each team plays 7 matches, so the answer will be 8 times 7. But doing it like that, we're in fact double counting. So the answer should be 8 times 7 over 2, which is another way of 8 times 7, which is another way of working it out. And if we generalize that, we get this. And it's kind of a different way of doing it, which Gauss did, is to say that if we add up the natural numbers, and then we add them up underneath backwards, and we get these each pair adding to n plus 1, and the n pairs, then we're going to get a final answer of n plus 1 over 2. So sort of 3 different ways of thinking about the same thing, of summing some numbers and arriving at the same result. How many ways can we take 2 things from 5? Well, this is a combination. It's actually not in the core maths syllabus. It's in the further studies stats syllabus. But in fact, there's a way in which we can think of this just using core maths, because the answer to this question is exactly the same as how many ways can we arrange those letters ABBA, 3 B's and an A in ABBA, 3 B's and 2 A's, sorry. And the reason being is that what we're interested in answering the second question is just how many positions can we put the 2 A's in. For example, they're in position 1 and 5. It wouldn't make any difference if they were in 5 and 1 because they're identical, all right? And we can also see here why 5 combination 2 is in fact going to be exactly the same as 5 combination 3. The B's in this case, when we're positioning the A's, are just kind of placeholders in a sense. So these two things are going to reveal exactly the same answer. This will also be 10, right? And the way we would do this in kind of high school maths is we'd say, well, we've got 5 letters in total, so it'd be 5 factorial, and then we need to divide by 2 factorial for the sort of double counting of the repeated A's, and 3 factorial for the double counting of the repeated B's. And lo and behold, we get exactly the same answer. Right, here's a product rule derivative. And there's no rocket surgery, I like to call rocket surgery combination between rocket science and brain surgery, higher order still. There's no rocket surgery to this, but basically our product rule, just to show and reinforce with learners that these things hold in kind of all circumstances. So for example, the derivative of 7x squared, if we choose to see that as a product, which is not an obvious thing to do, but if we do, and we use our product rule, then it's the derivative of 7 times x squared plus the derivative of x squared times 7, and the derivative of 7 is 0, and we get the answer that we would have expected from the outset. In similar vein, a compound angle identity here and a reduction formula. I think it's useful and important to show students, not that we want them to do it like this, but to show them the consistency that applies here. Sine of 270 cos theta plus cos of 270 sine theta. If we put in the values for sine and cos of 270, we get exactly the result that we would have got from our reduction formula, which is obviously the more efficient and better way to do it. Right, this is something that I think people will be very familiar with, but obviously there's a whole number of ways that we could find the turning point of a given parabola, right? I like to reinforce with this one on the left here the fact that this parabola is actually just ax squared, and it's been shifted to the left by b over 2a, right? With the result that its turning point, the x-coordinate of its turning point is minus b over 2a. Obvious advantage of completing the square is that we get the full turning point, both the x and the y coordinate. Another way would be to average the roots, right? They're the roots of the parabola, and if we average those, we get negative b over 2a. A third way would be to make the derivative equal to 0, and I think often we sort of neglect to show we get this formula minus b over 2a in the early years, and then we neglect to sort of just tie up the loose end when we've done the calculus, that this is just the derivative equal to 0, and that happens when x is negative b over 2a. At the same time here, I think it's worth looking at the second derivative and establishing that the second derivative is in fact just 2a, and therefore the concavity of a parabola is dependent entirely on the value of a. Right, in the early years, we tell them kind of if a is negative, it's a sad parabola. If a is positive, it's a happy parabola. In fact, as far as we know, parabolas have got no feelings whatsoever, and it's all to do with concavity. And the concavity is determined entirely by the sign of a, as we can see in the second derivative, which is just 2a. Right, here's a nice optimization problem. We're trying to find where on the parabola is it closest to that 0.41, right? And as you know, we in core maths we try and minimize the square of the distance. All right, so we find an expression for the square of L, we simplify it, and then ultimately we differentiate it, equate it to 0, and solve, and we get that x must be about 1,647. Another way of doing this question, which still relies on some calculus, is to actually appreciate that for the shortest distance, we should head perpendicularly to the curve from the 0.41. Right, now we know the gradient of that red tangent line is 2x, right? And we can also work out the gradient of the dashed line and get an expression for that. And the product of those two gradients must be -1 in order to have a 90-degree angle in there. And lo and behold, if we solve that equation, we get exactly the same answer. Right, I think a lot of us teach that loans are all about present value and savings are all about future value. Right, here's a loan question. So what are the repayments when 100,000 Rand is paid back with monthly repayments starting 1 month from the date of the loan, with the interest as follows? Right. I think the obvious way of doing this question is to work out the present value of all the payments and make that equal to the loan value, and we get 2,224 Rand and 44 cents. But there's an alternate method which doesn't rely on any present value at all, and that's to appreciate that when the loan is paid off, the loan with interest after 60 months must equal the future value of the payments that have been made. Right, and this, I think we're more familiar with seeing this as with a minus sign here in terms of getting our outstanding balance. But obviously, after 60 payments, the outstanding balance must be 0. So we've sort of added this across, and lo and behold, if we solve that equation, we get exactly the same answer. I think doing questions like this in kind of two different ways, two different formulas, two different ways of thinking about it, and then getting the same answer is powerful conceptually. I think it's encouraging, but it also sort of ties up the fact that maths makes sense. It always makes sense. Izibalo zikrateke injalo. Maths was invented by humans for humans to solve problems in our everyday lives. All right, and then finally, just something fun to end off with. Imagine paper which remains similar when one folds it in half. So we've got a piece of paper here. We'll give it dimensions of x by 1. We're going to fold it in half. And what we want is that blue rectangle on the left is similar to the original rectangle. Well, obviously the dimensions of the blue rectangle are 1 by x over 2. And if we take the longer side in the original rectangle, x divided by the shorter side, we must get the same as if we take the longer side in the blue triangle divided by the shorter side. When we solve this, we actually get the square root of 2. So the length of the paper must be the square root of 2 times the width. All right, and the square root of 2 is actually 1,41 or 141%. And you'll know that when you go up to a photocopier and you want to double the size of a piece of paper, the setting is actually 1,41 or 141%. When you want to halve it, it's 71%, which is the reciprocal of root 2. And that's because when we double the page, this dimension must increase by a factor of root 2, and so must this dimension. So we actually get root 2 times root 2, which gives us a doubling up of our area. Now, the paper that we write on every day actually has this property. Our A4 or our A paper range has the property that when you fold it in half, you get a rectangle that is similar. Just another little interesting thing that while we're here is that a piece of A0 paper actually has an area of 1 meter squared. All right, it has that property where its length is root 2 times its width. All right, A1 is half a meter squared, A2 a quarter, A3 an eighth, and A4 a 16th of a meter squared. Right, and so an interesting way to visualize a meter squared is to just get 16 pieces of A4 paper and lay them on the floor in any format you like. Obviously, don't overlap them, but that will give you a meter squared. All right, interestingly also, the paper that we write on, the sort of standard photocopy paper, is actually 80 grams per square meter, which means that a piece of A0 weighs 80 grams, A1 40, down to the paper we write on every day is 5 grams. So if you want to kind of quickly weigh something, if you've got 100 pieces of A4, 500 grams, all right? A ream of A4, 2.5 kilograms, and a box of photocopy paper, 12.5 kilograms. All right, guys, thanks very much for listening. I hope that you found that interesting and useful, and I hope that there might be just even one takeaway for one person, in which case it will all have been worthwhile.